There are more things likely to frighten us than there are to crush us. We suffer more often in imagination than in reality. By Seneca. Today, we're going to look at contact forces. So, a man pushes 3 boxes with an applied force of 100 newtons. 100 newtons. And assume there's no friction in the system. The boxes are lying on the floor, but there's no friction. What is the contact force between box A and box B? So, how much force is box A and box B pressing each other, and how much force is box B and box C pressing each other? Give this question a crack. I'll give you a moment to pause. And now, here's my solution. So, whenever we're dealing with problems like these, we should always draw free body diagrams. And there's also one thing we need to draw, which is a rosetta. So, make sure to copy down this diagram right here. Copy it down in your notebook right now. Okay, so let's scroll down and we're going to continue. So let's draw a rosetta. We know that this way is positive, this way is negative. And let's start with our free body diagrams. So first we should start with a free body diagram of the whole system. And now why is that? It's because we know that there is a net force being applied to this whole system of 100 newtons. Right, 100 newtons right here. And that makes it really easy for us because that means we can find the acceleration. We know the mass of the system is equal to 6 kilograms plus 7 kilograms plus 3 kilograms. So let's go down here. Let's draw a box. This is a super box. This box isn't just a normal box. It's a super box. And this box, you can imagine it as containing all of the boxes in one small box. Its mass is equal to 6 plus 7 plus 3, which is equal to 16 kilograms. And we know that the force net applied on it is equal to 100 newtons. So let's draw our arrows. This is the only relevant force. There's also gravity and normal force, but they cancel out. So this is the only force, which is the applied force of the person pushing it. And he's pushing to the right. So now that we know what force is and what mass is, that means force equals mass times acceleration. 100 newtons is equal to 16 kilograms times acceleration. Acceleration is equal to 100 divided by 16, which is 6.25 meters per second squared. And it's positive because it's to the right. All right. Now we've put in the first missing piece of the puzzle. Now, how do we continue? Well, let's see. How can I put? Okay. We continue by drawing a free body diagram of box A. Let me just check this isn't blocked. Okay. So if we look at box A by itself, what is really going on with box A? Well, box A is being pushed by the applied force. Yes, we see because the person. Let me magnify the person right here. This tongue out. He is pushing with his arms. He's pushing box A, right? So the force is going this way. The force is going to the right. Now, if we go back to this free body diagram, there's another force acting on box A, and that is actually force of box B on A. Now, this is very important because because box A is pushing on box B is also pushing on box A. And this is Newton's third law, which is that every force must have an equal and opposite force or something. And the reason why we put box B on box A is because this is going in the negative direction, right? Box A is also pushing on box B, and that's not the same as this applied force. Make note of that. But box A, box B on A is in the negative direction, and that is actually the contact force we're looking for. So we can solve for this by going 100 newtons. We're trying to find the net force. So the net force of box A is equal to force of B on A, which is negative, plus force applied, which is, we can now substitute because we know that the applied force is equal to 100 newtons. And however, we don't know what the force of B on A is yet. What else do we know? We can figure out the net force because we know that block A weighs 6 kilograms and its acceleration of A, because we know that the system acceleration is 6.25 meters per square second. That's the same for A. They're all moving, right? They're all moving and accelerating at the same time. So we can say that the acceleration is uniform for all of the blocks. So it's a bit small. Now, what does this leave us? This leaves us with FB on A. This is still the variable that we're trying to find. Okay, so let's do some calculations. 6 times 6.25 is equal to 37.5 minus, now let's bring this 100 newtons over. Which is equal to FB on A, which gives us a final value of negative 62.5 newtons. Now, most of these questions will be asking you for the magnitude of the contact force because it goes both ways, right? FB on A, right? B on A is equal to negative 62.5, but Newton's third law says that FA on B would be 62.5, right? Equal in magnitude, but opposite in direction. So this is our first contact force, which is 62.5 newtons. Now let's begin on the other one, right? So we looked at A and B at contact force. Now let's look at B on C. So the easiest way to do this is to just draw another free body diagram. FBD, a free body diagram of B. Now, what are the forces acting on block B? Oh wait, let me draw that again. That was a bad square. This is somewhat better. Okay. So, this time, and this part is actually FA on B. So, let's do the calculations. F net equals FC on B plus FA on B. Now, mass times acceleration is equal to, we don't know C on B yet, but we do know A on B, because let's go from here. A on B is equal to 62.5 newtons. And this is our unknown. Okay. Now for the net force, we know that it's 7 kilograms times the acceleration of 6.25 meters per second squared. Is equal to FC on B plus 62.5 newtons. Now, let's whip out the calculator and we get that 7 times 6.25 is equal to 43.75 newtons. Now, minusing 62.5, we're bringing this to the other side. We're bringing 62.5 newtons to the other side. And this is equal to FCNB, which is equal to negative 18.75 newtons. And again, typically the questions you're going to get are going to be asking for magnitude, so you can just give the final answer of 18.75 newtons. And of course, if there were sig digs in this question, you would round to the appropriate sig digs. Okay, that is how you solve this problem.